This is the Chapter 3-4, Part 2, Commentary, and we're going to talk about oxidation reactions of alcohols. So we're going to focus on starting off with an alcohol, such as this example that I'm circling right here, and we're going to predict the product after oxidation has occurred. We're going to go ahead and define oxidation as either the addition of oxygen or the removal of hydrogens. And it's possible to have both occur at the same time. But in general, one's going to be added or the other one's going to be removed. The oxygen is going to be added or hydrogens are going to be removed. Anything that causes oxidation in our target reactant we call a oxidation agent. The oxidation agent is going to be represented as an O. As previously mentioned, common oxidation agents such as a silver ammonium ion, PCC, also known as pyridinium chlorochromate, or chromic acid. That's the precursor to the infamous Aaron Brockovich cancer-causing catalyst. Hence, chromic acid isn't, although it's still used in chemistry, chromic acid is kind of frowned upon nowadays. But those are all examples of oxidizing agents. The problem with this is, in this level of chemistry, those can get kind of complicated when we show them. So we're going to make it really easy, simplify it so there's less stuff to worry about, which makes me feel really good. So in this case, we're just going to represent all oxidizing agents as the letter O. Now, you will then have to reason out that if you see this O, that means you're going to go ahead and lose hydrogens or gain oxygen. So in this example that I'm circling right here, we're going to go ahead and lose, and I'll X them out, or cross them out. We're going to lose 2 hydrogens. This will then leave missing 2 hydrogens, and those bonds that were connected to those hydrogens are going to form a second pi bond. So it'll form a second bond called a pi bond, which I've tried to circle here. So let's go ahead and figure out how we're going to do each of these reactions. What I will do on future tests and exams, I will give you the starting reactants, such as what I'm circling here, and I'll indicate that it's an oxidizing reaction by simply putting this O right here. I'm not going to put the name of the reagent, that'll just be confusing, and there's a lot of side reactions that we would need to do in order to explain it, so I'm just going to put the O. You'll then need to go ahead and predict the proper product. Now, the first thing you're going to do is you're going to figure out, is my starting reactant, and I'm going to highlight this, is it a tertiary alcohol, a secondary alcohol, or a primary alcohol? Tertiary alcohols are connected to carbons, which are connected to 3 other carbons. Secondary alcohols are connected to carbons, which are connected to 2 other carbons, and primary alcohols are connected to carbons, which are connected to only 1 other carbon. So in this instance right here, let me go ahead and erase all these marks. We would first figure out that this molecule right here is going to be a primary alcohol because this carbon is only connected to 1 other carbon. We just write an R here because we don't show how big and how substituted the carbon is, but it's only connected to 1 other carbon. Whereas this molecule down here, it's connected to 2 other carbons, which my red arrows are pointing to. Let me go ahead and give you an additional example as a point of reference. In this top example that I'm lassoing, that's a primary alcohol because it's connected to only, this carbon right here is connected to only 1 other carbon. Let's go to the next example. The alcohol is a secondary alcohol because the alcohol that this carbon is attached to is attached to 2 other carbons. 1 and 2 other carbons. I'm going to go ahead in the secondary alcohol and highlight the 2 carbons that it's connected to. So what I'm going to do is just highlight the entire molecule. Make it a little bit easier on myself, so you can see everything. Oops. Let me take that back. I'm just going to highlight the carbons. Give me 1 second. I'm going to highlight the carbons and hydrogens. There we go. Let me go ahead and create a temporary new page, and I'll blow this up so that way you can see a nice example right here. I'll make the font a little bit smaller. There we go. Now, this alcohol again is connected to this carbon right here. It's this carbon that we're going to look at that I'm highlighting, and this tells us whether it's a primary, secondary, or tertiary alcohol. To figure out if it's a primary, secondary, or tertiary, we figure out how many other carbons is it connected to. In this case, it's connected to 2 other carbons. So in this case, I'm going to go ahead and highlight the number of carbons in red. So in this case, this is going to be a secondary carbon. Going back to our example, what I'm going to go ahead and do is move everything over just so I can show you this molecule right here. I'm going to go ahead and keep it at this point in its condensed form. I'll explain why later. Let's go down to tertiary alcohol. So this alcohol is connected to this carbon right here. This is a tertiary alcohol because this carbon is connected to 1, 2, 3 other carbons. I'm going to go ahead, again, circle this. Open up a new sketch. Going to increase the size and show the carbon and hydrogens. Oops, lost my alcohol. So this carbon is connected to 1, 2, 3 other carbons. I'll go ahead and highlight the carbons in red. So therefore, it's a tertiary alcohol. Now, going back to our original example, so in this top one, first thing we need to figure out is if a alcohol is a primary, secondary, or tertiary alcohol. So in this case, the alcohol is connected to this carbon right here, and this carbon is connected to only 1 other carbon, so therefore it's a primary alcohol. Now, first thing you want to go ahead and do is either draw it out or mentally picture what does this molecule look like in its condensed form. So I'm going to go ahead and, rather than have you mentally picture it, I'll just go ahead and have you see it so you can see everything. So there's a molecule right here. We then need to count how many carbons, I'm sorry, I take that back. We need to count how many hydrogens are connected to the alcohol bonded carbon. So in this case, I'm going to go ahead and highlight this in blue. We need to figure out how many hydrogens are on this alcohol bonded carbon. So the alcohol has to be directly bonded to it. This is the alcohol bonded carbon. It's also known as the alpha carbon, but we'll focus on that later. So right here we have our carbon right here. The alcohol bonded carbon. It has two other hydrogens. Now, it turns out that for an oxidation reaction to occur, we need to only remove these hydrogens. So we can't remove carbons. It has to be hydrogens we remove. The leftover or the leaving hydrogens will then create extra space for us to go ahead and form brand new bonds. So these are the only hydrogens that we can mess with. The other hydrogens we can mess with are directly on the alcohol hydrogen. We cannot, however, mess with any other part of the molecule. So, in summary, we can only mess with the hydrogens on the alcohol bonded carbon, and we can mess with the hydrogens on the alcohol itself. So let me go ahead and highlight this in blue. We cannot mess with the rest of the molecule. So let's go ahead and go to the secondary alcohol, just keeping this in mind. I can only mess with the hydrogens that are directly on the secondary alcohol. Secondary alcohol carbon, so this carbon right here. I cannot mess with any other hydrogens. On this tertiary carbon, here we have a dilemma. Do we see any other hydrogens that are directly attached? Let me go ahead and turn all of this into a condensed structure just so you can see what I mean. So a little crowded, but here is the carbon we're looking at. I'm going to go ahead and highlight this in blue. So in this case right here, this carbon on this tertiary alcohol has no other hydrogens attached. And it can't if we obey the 4-bond rule. So the only other hydrogen that can be affected is this one on the alcohol, but we need hydrogens on the carbon for any of these reactions to occur. So automatically, if we look at the tertiary alcohol, we're going to assume that no reaction can occur. So think of this as a trick question. Now, our reason for this is in order to form a carbonyl group, we need to have a double bond. Unfortunately, these carbons that are directly attached can never come off. Consequently, you cannot have a second bond, a pi bond attaching. So therefore, no reaction can occur. Now, if we move up to this molecule right here, the secondary alcohol, here one of the hydrogens can come off, this one in blue. And as I said before, the alcohol hydrogens can come off, and I'll go ahead and highlight this one now in blue. So this hydrogen can come off. So in order to form a pi bond, we need to have two of these hydrogens come off, and now we have our nice carbonyl group. and I'll highlight this in blue. If we go up to our primary alcohol, notice we have two hydrogens that are present on our alcohol bonded carbon, and of course the hydrogen on that alcohol right here. So consequently we can have two individual reactions, one right after the other. Now I'm not going to do that to you. I'll only ask for one product at a time. But be prepared to see that product as a future reactant, and I'll show you that in a second. So let's go ahead and do all of these reactions. In the secondary alcohol, the hydrogen on the carbon and the hydrogen on the oxygen are going to leave, and they're going to form a brand new pi bond. Just to highlight this right here, I'll go ahead and show you the carbon. So here's the carbon. Oops. Turn that back into an oxygen. Where's the oxygen? Ah, there you go. So voila. And the hydrogens that had come off will go ahead and form hydrogen gas, H2. And I'll highlight this in blue. Let's go over here. I'm going to have one hydrogen come off on the primary alcohol, on the carbon, which the alcohol is bonded to. So this is a primary alcohol, one hydrogen coming off. Here I'll have one hydrogen coming off, and I'll go ahead and form an aldehyde. So let me go ahead and copy this one over just so you can see what's happening. So I'm going to go ahead and add in a double bond. The minute I do, notice how two hydrogen had to be removed. And consequently, it's going to form a hydrogen gas molecule. So let's go ahead and practice. I've given you a lot of details, but let's see these in motion. In this first one right here, notice we're focusing on the alcohol. I'm not going to give it to you like this. I'll give it to you with the indication that it's going to be an oxidation reaction. And how do I do that? Look at the O. Look at the O. Might as well highlight this in red. Look at the O. So that's the oxidating agent. Now, let's go ahead and take a look at the carbon that's directly bonded to this alcohol. So I'm going to go ahead and highlight this carbon right here. Actually, I'm going to highlight all of these carbons right here. And you can do this in your mind. You can do it on the piece of paper that's near it. So in this case, this right here would be classified as a secondary alcohol. And that's because the alcohol bonded carbon is connected to only two other carbons. So it's a secondary alcohol. And I'll highlight those in red. Consequently, here we have one hydrogen here, and we have the alcohol hydrogen here. So this can only form what we call a ketone. The carbonyl can only form a ketone. So I'm going to go ahead and add in a double bond here. Notice how the hydrogens disappear. It's the only way we can obey the 4-bond rule on the carbon and the 2-bond rule on the oxygen. So let me go ahead and undo that. I'll go ahead and make a picture over here. I'll add in a double bond here, consequently removing those two hydrogens, and voila. And then I have to go ahead and show, and I'll make copies up here really quick. Oops. So, and then you have your two leftover hydrogens. So, this right here is an example of a ketone. A ketone. I do want to point out, and I'll highlight this in green, that those molecules right there in green, or excuse me, those atoms in green, these right here, think of this as window dressing. Even though they're branches or substituents, if you will, and the fluorine is actually considered a functional group, these are just window dressing. They do not participate in the reaction. And at most, they're just there to try to trick you. So please ignore those. Although they're written in the final product, there is no changes to them. Let's go to the next one down here. This is an example of a let me go ahead and show you everything. So yeah, even though I have it written to the side like this is an example of a primary alcohol. Yeah, it looks a little confusing, but keep in mind this carbon right here is connected to only one other carbon, and I'll highlight this in red. I'll also show it. It's only connected to one other carbon in red. I should probably show the hydrogens on that. Alright. So this would make this one a primary alcohol. A primary alcohol. I'll write this to the side. Now, this one's a little bit more tricky. So again, you're going to remove one hydrogen from the alcohol, one hydrogen from the carbon. When I do that, it's going to go ahead and form a brand new double bonded carbon oxygen known as a carbonyl group. However, because it's on the end, so let me go ahead and do that. Because it's at the end, this is known as a aldehyde. A aldehyde. So, this aldehyde right here, so here's our aldehyde. Even though we had two hydrogens come off, if you notice, we have an extra hydrogen that's still present. So it turns out there could be another reaction that may occur down the line. In this case, I wouldn't actually make you do two back-to-back reactions like this. What I could do, however, is I could give you something which would produce a product that looks like this. This is the acid. So what I'm going to do is I'm going to erase this one right here. I'm going to go ahead and take this one right here, and I'm going to create a brand new question. And here's my starting reactant. Here's my oxidation agent. Whoops, you know what? I didn't even have one here, did I? Let me put that there. Here's my oxidation agent. And I'm going to go ahead and do one more oxidation reaction. The aldehydes will always form an acid. This is a really weird product. So basically what we're going to do is we're going to stick an oxygen between this carbon and this hydrogen right here. and I'll highlight this in magenta. So in this case right here, this carbon and hydrogen is present, and when I oxidize it, I'm going to stick one oxygen between this carbon and hydrogen. So it's going to look like this. And voila, there is our final product. So notice this one right here. This is an aldehyde, and it went ahead and it formed what we call a carboxylic acid. Now, I could ask you to name these over here, which I think would be pretty easy. So this would be a 2-fluoro 3-ethyl 1, 2, 3, 4, 5, 6, 7 heptanone. And alphabetizing it really should be 3-ethyl 2-fluoro heptan 4-one. Excellent. And this one over here, this is going to be a aldehyde. So just by looking at it, it would be 2-ethyl pentanol. Keep in mind, if you see no 1 here, the 1 is implied, since aldehydes always occur at the very end. And then finally, we have our acid. I haven't taught you how to do acids yet, so do not worry about that. I should go ahead and put that on there. And voila, we have our carboxylic acid. I could ask you to sketch the final product, giving you this structure right here with an aldehyde, but I'm not going to get crazy on that. I wouldn't actually have you name it, at least not until we get to those chapters. I've gone into explicit detail on this. So going back to our slides, automatically primary alcohol. Why? Because the alcohol bonded carbon, we call it an alcohol bonded carbon because the alcohol is bonded to this carbon. The alcohol bonded carbon is only connected to one other carbon, so therefore it's a primary alcohol. Compare it to this one over here. This is a secondary alcohol because the alcohol bonded carbon is connected to two other carbons. For primary alcohols, they form a aldehyde, and then if this was my starting reactant, the aldehyde would form a carboxylic acid. For secondary alcohols, it starts off as a secondary alcohol forming a ketone. A big hint that no other future reactions can occur is that there are no other hydrogens directly on the carbon. So I know that ketone is the end product for this secondary alcohol reaction, and the carboxylic acid is the end product for the primary alcohol oxidation reaction. Now, we love using various reagents. This right here is a oxidation reagent. So you can see just how complicated the molecule looks, this polyatomic ion. It's one of the reasons why we choose not to give you the reagent, we just give you the O. But in this case, it's going to go ahead and form a really weird acid, what we call an acid salt. And this acid salt will actually release silver, and it'll actually create silver plating on the glass itself. So what do you need to know about this? Absolutely nothing. You can scratch this out. Just wanted to show you what the reaction looks like. This reaction down here is another really cool oxidation reaction with copper, and it creates a nice red precipitate. Do you have to know this? No, you can cross this out. So what do I need to to know in this slide right here. You need to know that these are used to test for the presence of aldehydes. And the name of the first reagent is called Toland's reagent. The name of the second reagent is called Benedict's reagent. So this is Toland's agent right here. This is Benedict's reagent. These are used to test for aldehydes. If it turns out there's silver or a blackish silver coating on the inside of your test tube, then it's positive for an aldehyde. If you have an aldehyde and you add in Benedict's reagent, and there's a red precipitate, then, and we'll get into specifics later, but if you have that, then you have a aldehyde. So know the reagent names and know what a positive test is for, and know what type of qualitative observation to look for. In this case, the name is Toland's reagent, Benedict's. The test is for positive if aldehyde is present. If aldehyde is present, and then the qualitative observation you're looking for, Toland's is silver coating, Benedict's it's a red precipitate that appears. Moving on, I could give you a question like this, and you should be able to answer it. And let's move on. These are reduction reactions. Reduction reactions. So I'm actually going to write that on here. These are reduction reactions. Reduction reactions are when you add in hydrogen gas. Notice there's two hydrogens, and I'm just going to rewrite the hydrogen gas right here. One hydrogen is going to go on top, the other hydrogen is going to go on bottom. Yes, there is a mechanism to this, and it's not as straightforward as I just showed you right here, but again, we're just going to be looking for final products in this course. So in this case, this is before, and then this is after. Just like with alkenes, it's nice to have a catalyst to help speed this up. In this case, we add in the platinum catalyst. You may or may not see that. However, the big hint that this is a reduction reaction is if you have a H2 as your starting reactant. So in this case right here, if I give you an aldehyde, it's going to form a primary alcohol. If I give you a ketone, it's always going to form a secondary alcohol. Here are common examples. I think this is pretty easy, so I'll only give you two of them. But in this case right here, propanol, the hydrogen splits up, putting a hydrogen on top here, putting a hydrogen to the carbon here. Consequently, it forms a primary alcohol. Acetone, this is a secondary alcohol. Hydrogen goes on here, the other hydrogen goes down here, so it forms a secondary alcohol. So acetone always forms a secondary alcohol. And then propanol always forms a primary. The other name for this is a ketone. And let me just say that one more time in case I made a mistake. The ketones will always form the secondary alcohols, and in this case, this right here is an aldehyde. The aldehyde will always form a primary alcohol. So primary, and then just down here is going to be a secondary. Hey, what about tertiaries? Well, unfortunately, tertiary alcohols, they don't have enough hydrogens to be evicted in order to form a carbonyl group, so no reaction.